here we're going to talk about limits to infinity. So we've been taking limits so far to certain numbers, like limit as x approaches 4 of some function. Here, instead, we're going to do limits as x approaches infinity. And to start that, we'll look at a couple graphs. First, we have the graph of y equals 1 over x. And on this, you can see as x goes to infinity, the function is approaching the line y equals 0. So as x goes to infinity, this curve keeps going down, but it never hits 0, and it never goes over 0. So in this case, we would say the limit as x goes to infinity of 1 over x is 0. You could also see that algebraically by taking 1 over x. You put x equals 10 in, and you get a tenth. You put x equals 100 in, you get a hundredth. X equals a million, you get a millionth. And as x is getting larger, you see this term gets smaller and smaller. And the limit as x goes to infinity of 1 over x is 0. Now, with the algebraic limit laws, we could extend this actually. We could raise it to the n power for n larger than 1. 0 to the n is 0. So if n equals 1 is up here. But for n larger than 1, we have that same result. Actually, that should be n larger than 0. You could do that with fraction numbers too. Like 1/2. That limit would also be 0. But not 0, because that limit would be 1. And similarly over here for the line y equals x, you can see with the graph, as x goes to infinity, this function just goes off. It keeps going higher. So in this case, as x goes to infinity, this function goes to infinity. So as x goes to infinity, x goes to infinity. And we can extend this the same way over there by doing x to the n, the algebraic limit laws. And that limit would also be infinity for n greater than 0. Now, these four observations, these 4 limits, we can actually use to compute a lot of limits. And what we're going to do in the next 6 examples is see how we can use algebra to force terms like this to appear as we take certain limits as x goes to infinity. So let's do those examples now. So first, let's do this example. Limit as x goes to infinity. Let's do a rational function. So a polynomial over a polynomial. Limit as x goes to infinity, 2x squared plus 3 over 5x squared minus 4x. And what we're going to do for all of these is immediately multiply by a 1. So we have x goes to infinity, some rational function. We're going to multiply by 1. Now, which one are we going to multiply by? Well, we look at the denominator. This process will work for all of these. You could do similar arguments if you replace denominator with numerator. But we'll stick with denominator. You look at the terms on the denominator. You look at the largest degree of x. Here we have a degree 2. Here we have a degree 1. So degree 2 is the largest degree on the bottom. And then you multiply everything by 1 divided by x to that degree. So in this case, the largest degree on the bottom is 2. So we'll multiply everything by 1 over x squared. Multiply everything on top by 1 over x squared. Multiply everything on the bottom by 1 over x squared. Right here, all we're doing is multiplying by 1. But we will see that this will force lots of those terms to look like those first four limits. So let's multiply this out. It still equals the limit. On top, multiplying everything by 1 over x squared is the same as dividing everything by x squared. 2x squared divided by x squared is just 2, because the x squared and the x squared will cancel. 3 times 1 over x squared is just 3 over x squared, because no x's are going to cancel. Similarly down here, 5x squared divided by x squared, 5x squared divided by x squared, well, you have an x squared up there, and you have an x squared down there. So that just equals 5, similarly to why that equaled 2. And then negative 4x times 1 over x squared is negative 4x over x squared. And here, one of those x's is going to cancel. The negative 4 won't cancel, but an x will cancel from the top, and an x will cancel from the bottom, and you're left with an x on the bottom. And you can see from doing that, we can now take limits as x goes to infinity on all of these terms because, well, as x goes to infinity, 2 goes to 2. As x goes to infinity, 3 over x squared. Well, that's 3 times 1 over x squared. We know 1 over x squared from the observation over there. 1 over x squared as x goes to infinity is 0. 3 times 0 is 0. And on the bottom, as x goes to infinity, 5 does not change. And as x goes to infinity, this is negative 4 times 1 over x. Negative 4 times 0 is 0. So here we have, this limit is 2/5. And all we did from the start, we had a limit as x goes to infinity. We multiplied by 1. We multiplied by a convenient 1. Let's look at another example. Limit as x goes to infinity. Negative 3x to the 21, negative 7x to the 10, all over 7x to the 21 plus 4x to the 18th minus 3. So here we have the same thing. We have a rational function, polynomial over polynomial, and we want the limit as x goes to infinity. Well, we look at the denominator. The largest degree on the denominator is 21. So we'll multiply everything by 1 over x to the 21. Divide everything by x to the 21. And here, I guess I'll go down instead of over. Yeah, I'll go down instead of over, so it won't be perfectly parallel to that. This equals, what does this equal? The limit as x goes to infinity. We still haven't taken a limit. Divide everything by x to the 21. Well, if you have 21 x's on top and 21 x's on the bottom, you're left with no x's. If you have 10 x's on top and 21 x's on the bottom, well, 10 of them are going to cancel. And you're left with 11 of them on the bottom. Down here, 7x to the 21 divided by x to the 21 is just 7. 4x to the 18 divided by x to the 21. Well, we have 18 x's in the numerator, 21 x's in the denominator, so that leaves us with 3 x's in the denominator, and that 4 stays there. And with this negative 3, nothing is going to cancel, so we're just left with a negative 3 and 21 x's in the denominator. So we divided everything by x to the 21st, and now this term goes to 0, because it's just negative 7 times 1 over x to the 11th. And as x goes to infinity, x to the 11th, well, as x goes to infinity, 1 over x to the 11th goes to 0. This also goes to 0. This also goes to 0. Negative 3 and 7 go to negative 3 and 7. Fill that out like that, putting the zeros like that. And then, of course, that just equals negative 3/7. So now, in these first two examples, the degree of the polynomial on top equaled the degree of the polynomial on the bottom. So here, the degree on top was 2. The degree on the bottom was 2. Degree means the highest exponent in general. When someone says the degree of a polynomial, they mean just the largest exponent. So this up here, degree 2, degree 2, degree 21, degree 21. Well, what happens if we change them around so that, for example, we could have something where the degree on top was less than the degree on the bottom? Well, in that case, we'll still follow the same first step. We'll still multiply by a convenient 1. We'll still look at the denominator to figure out which convenient 1 to multiply by. So let's take this one. Limit as x goes to infinity, 4x cubed minus 7x over 6x to the fourth plus 5x minus 2. Well, we still have a limit as x goes to infinity of a rational function. So we're going to look at the denominator and find the largest exponent. The largest exponent is 4. So we'll divide everything by x to the fourth. Or we'll multiply everything by 1 over x to the fourth. I'll go down this time too. So this equals, well, what does it equal? Divide everything by x to the fourth. Well, here, 4x cubed over x to the fourth, well, 3 of those x's go away. So you're left with just 1x on the bottom. 7x over x to the fourth, well, the 7 stays there, but one of these x's is going to cancel. So you're left with 3 x's on the bottom, and it's negative 7, so I should put negatives on everything. And do the same multiplication on the bottom. We have 6x to the fourth divided by x to the fourth. Well, that's just 6, because all of the x's will cancel. Plus 5. This time we have 5 over x cubed, because we have 1x and 4 x's, just like up there. And then negative 2 over x to the fourth. No x's will cancel there. Well, now look what happens when we take the limit as x goes to infinity. This term, 4 over x as x goes to infinity, that just goes to 0, because it's 4 times 1 over x. Negative 7 over x cubed also goes to 0. Well, that's great. We know if we have a limit that gives us 0 over 0, then we can't compute it without additional algebra. But if we have 0 over a number, well, that's just a fraction that reduces to 0. So let's see what we have. As x goes to infinity, 6 goes to 6. 5 over x cubed also goes to 0. Negative 2 over x to the fourth also goes to 0. So this goes to 0 over 6, which is just 0. So we have this limit is 0. Let's do another. Let's do this one. This example, notice the degree on top is 3, degree on the bottom is 4. So the degree on the bottom is larger than the degree on top. 3 x to the 7 plus 4. So the first two examples, the degree on top equal degree on the bottom. The second example, degree on top was less than the degree on the bottom. This next example, the degree on top will be larger than the degree on the bottom. So let's do this limit. We again have a rational function. That's what we will take limits of here. When we have that, we look at the denominator. The largest exponent here is 5. So we'll divide everything by x to the 5th. We take that limit. I guess I'll go down this time. We take this, well, we don't take the limit. We do the distribution. Well, here we have negative 3 x to the 7th divided by x to the 5th. So we have 7 x's on top and 5 x's on the bottom. That leaves us with 2 x's on top. 4 times 1 over x to the 5th. None of those x's are going to cancel. Now in the bottom, 2x to the 5th divided by x to the 5th, well, all of those x's go away. So that's just 2. And then here, negative x over x to the 5th, the negative 1 stays, and so do 4 of the x's in the denominator. We multiply everything by 1 over x to the 5th. Well, and what happens now? Well, actually, I don't need to write limit as x goes to infinity because we can take the limit. As x goes to infinity, this term goes to 0, 4 over x to the 5th. Negative 1 over x to the 4th also goes to 0. But what does the rest do? Well, maybe I should write out limit. Limit as x goes to infinity. We'll just get rid of those two zeros. So now we have negative 3 x squared over 2. Well, we could do a kind of substitution here and get that x squared goes to infinity, and you multiply that by a negative number, that becomes a negative infinity. I'm going to illustrate that in 2 steps, actually. So here you could do it in 1 step, equals negative infinity, because it's infinity times a negative number. But here I'm going to first just pull out the negative number. So it equals the same thing with negative 3/2 pulled out of the limit. And you're left with x squared. And this is negative 3/2 times infinity. Negative 3/2 times infinity is a negative infinity. Now, so we've had 4 examples. The first 2, the degree on top equaled the degree on the bottom. The third one here, the degree on top was less than the degree on bottom, and we got a limit of 0. That will always happen when we have the degree on top being less than the degree on the bottom. Down here, we had the limit on top being, or not the limit, the degree on top is larger than the degree on the bottom. And we got an infinity, meaning positive or negative infinity. That will also always happen when the degree on top is larger. In the first 2 examples, the degrees were equal and we got a finite number. That is also what we should expect. When you have degree on top is equal to degree on the bottom, your limit will be a finite number. Let's look at one more example like this one, where the degree on top was larger. Example. Limit as x goes to infinity, 2x squared plus 3 over x plus 1. So right here, we still have polynomial over polynomial. degree on bottom is 1. So we'll multiply everything by 1 over x. Degree on the bottom is 1. Divide everything by x. So do that on top, you get 2. You get an x, because 2 x's are on top. 1 is on the bottom, 1 will go away. Plus 3 over x, all over 1 plus 1 over x. And as x goes to infinity, well, this term goes to 0. This term goes to 0. So this just goes to limit as x goes to infinity of 2x over 1. As x goes to infinity, 2x also goes to infinity. So notice in these two limits, we have one whose limit was positive infinity and one whose limit is negative infinity. Now, why did that happen? Well, to figure out why that happened, let's look at the first two examples we did. So they are no longer on this board, but they might be in your notes. First two examples, the limit, the first one was 2/5. The second one, the limit was negative 3/7. And you'll notice, in the one whose limit is 2/5, there is a 2 and there is a 5 in the initial function. The 2 is the coefficient of x squared. The 5 is the coefficient of x squared. And that will work. However, you do have to go through the work. So you can't just look at the coefficients and say that's the limit. But you can observe, as a side observation, that that is the answer you should expect. The second one, we had x to the 21st on the top and the bottom. The coefficient on x to the 21st are negative 3 and 7. And that gave us our limit. So the coefficients on the largest terms seem to be quite influential. And they are, even in these two. Look at the largest terms here. 2 and 1. Those are both positive numbers. And we have a limit to positive infinity. The positive numbers don't change the sign of that infinity. Similarly, over here, the coefficients negative 3 and positive 2. Well, negative 3 and positive 2 turn this limit to infinity into a limit, well, they turn this limit, which is infinity, into a negative times that infinity, or a negative infinity. So even before doing any of the algebra, you might be able to figure out what answer you should expect. But you do have to go through the algebra. Let's look at another limit. So far we've had just rational functions. Well, what if we throw a square root on one of them? We can do that. Can we take the limit if we do that? Well, let's see. I said 6 examples, and we've done 5, so you might expect that, yes, we will be able to handle it. So let's see that. Limit as x goes to infinity of root 2x squared plus 5 over 4 minus 3x. Now here, we have a square root and we have some polynomials. One is under a square root. But what we are going to do is follow the same first step. And what was that first step? First step was look at the degree on the bottom, which is 1 in this case. And multiply everything by 1 over x to that number. In this case, 1 over x to the first. Well, if we do that, what do we get? Well, on the bottom, we get 4 over x minus 3. What do we get on top? Well, we have a square root there. How can we multiply so that a number gets under a square root? Here, we can't immediately distribute that in, and say that it's root 2x plus 5 over x. We can't distribute like that. We need to introduce a square root to this term so that it can multiply through the numerator. Well, what do we mean by that? Let's just block this off as side work for now. We need to do 2x squared plus 5, all under square root, divided by x. That's what multiplying by 1 over x is. Well, we can do that by rewriting this x using a square root. Now right here, that would allow this fraction to simplify, like this. That would allow for a simplification. That would allow for the denominator to get under the square root. But we can't do that, because this is changing the problem. What we're multiplying by is 1 over x. This is now multiplying by 1 over root x. So in order to leave it as a multiplication by 1 over x, we will write x as the square root over x squared, or as the square root of x squared. The square root of x squared is x. So right here, this is the same as that numerator, because we have this times 1 over x, well, that's the same as this divided by x, and x is the same as root x squared. And then this simplifies, to root 2 plus 5 over x squared. So root 2 plus 5 over x squared. So we multiply by 1 over x, and we rewrite that x as square root of x squared, so that we can simplify the numerator. Well, now all we have to use are the algebraic limit laws. Limits can get inside square roots. That was one of the algebraic limit laws. As x goes to infinity, 2 goes to 2. The square root stays there. As x goes to infinity, 5 over x squared goes to 0. As x goes to infinity, 4 over x goes to 0, and negative 3 goes to 3. Negative 3 goes to negative 3. So this simplifies to root 2 over, so it simplifies to negative root 2 over 3. I'll write that like this. Negative root 2 over 3. And again, you can make a parallel coefficient argument, because square root and x squared kind of act like x. So this kind of acts like an x over x.